it's convenient for Europeans as us and for Americans, but not for you. I know. So I think we are the only seminar that has some morning sessions. So I hope that's
recording in progress.
I think maybe we can start now.
Yeah, no, in principle you can if the speaker is ready.
Okay. And we have two speakers in this section. Our first speaker is Sebastian Cote from Institut Polytechnique de Paris, and he will talk about towards solid density electron beams, extremely dense gamma repulses, and strong field QED in beam plasma interaction. And you will have 25 minutes talk. If you are ready, you can start now.
Hello, everyone. Do you hear me well? Working well? Okay. Thank you. So in this presentation, I want to talk about similar science that can be done with extreme light, but leveraging instead the electromagnetic fields of electron beams with extreme parameters, rather than directly from laser pulse from a laser facility. So the presentation outline is as follows. I will start by talking about the most simple case of an electron beam that collides with a solid density plasma. And I will show that this can potentially allow us to probe the strong field QED regime with precision measurement. Then I will move to the case where the beam will collide with a sequence of solid density plasma, simply foils, and what can be done in that case, where the effect can be enhanced. And finally, in the third part, I will discuss what we are planning to do in an experiment at the SLAC Facet 2 accelerator facility. And all of this has been done as part of a collaboration, which is around this S9.4 experiment. And what I'm presenting today is the result of a very close collaboration between us at LOR and Max Planck Institute for Kernphysics, Heidelberg in Germany, and CEA in France. And for everything related to the experiment, all the hardware development, commissioning of diagnostics, and so on, we've been working very closely with SLAC as well. So let's start with part number one. So we'll start with the simple case of a single collision between the beam and the solid density plasma. And I'll talk about strong field QED first. So it has already been introduced in the previous talk. We have this quantum electron parameter chi that gives us the ratio between the field that is experienced in the rest frame of the electrons and the shrink of electric field, and that characterize the onset of strong field QED effects, such as nonlinear content scattering and nonlinear Brett-Wheeler pair productions. And as you know, there are many projects, and one has been presented just before me, that are based on a very high power laser facilities. In the literature, there was one possibility that was also proposed, which is a laserless scenario, that's proposed by Yakimenko and al., where two electron beams are used. And here, the way it works is that one electron beam will experience the electric and magnetic field of the second beam. So the source of the electromagnetic field are not the laser, but they are actually the beam. And so in that case, if you have extremely dense and high energy beams, you could potentially reach not only the strong field QED regime, but the fully non-perturbative regime with alpha tied to the power 2/3 greater than 1. So this is still extremely challenging to do, this type of collisions with high energy beams. And so here, the idea was to leverage the plasma, and we're doing many experiments involving plasma with laser and electron beams. And so here, by using a plasma instead of the second beam, we can have a process where when the electron beam enters the solid density plasma, the plasma is going to screen the cell fields of the electron beams that can potentially reflect these fields. And this can be understood, this reflected field, as the field of an image beam, which is shown here, which has opposite charge and opposite velocity. And so to some extent, by using this solid density plasma here, you realize not a collision between two beams, but a collision between the beam and its image. And so potentially you offer a significant simplification of the experiment because you only need one beam. But most importantly, you allow for automatic alignment between the beam and the fields. And even you have a nice fitting of the size of your fields and the size of the beam, so that you avoid the situation where, for example, the laser is much smaller or the fields are much smaller than the electron beam. And so for proof of concept simulation, here you see on the top left the electron beam. Below it, you see electric and magnetic field. And this is when you're in vacuum. So in vacuum, so here in the middle plot, you see different fields, the electric fields, the magnetic fields, and in black, you see the electric field in an electron rest frame over gamma, which can be translated to a chi value if you fix the beam energy. So here it's an example with 10 GeV. And you see that initially it is 0, and this is simply from the fact that E and B compensate each other when you're in vacuum. Then you get into, the beam is going to enter the plasma, which you see here. And when this is happening, you have almost a cancellation of the electric field and a doubling of the magnetic field here, as you expect if the fields are reflected, because in that case, the magnetic fields of the incident and reflected adds, while the electric fields cancel out to satisfy the screening condition. So it turns out that this is true in what I've just said is true in the radiative regime, where the longitudinal size is smaller than the transverse size for the beam. But actually, if you're in the stationary regime, you're in a case where the B field is the same as the B field of the incident beam, and it doesn't double. And so the final result is that as you go through these collisions with the boundary vacuum plasma boundary, the chi value goes up all the way to a maximum value of 5 here for 10 GeV beam, and then it drops again to 0 as the beam enters the plasma. So that's actually a very interesting situation, because if you know your beam well, then you know the cell field and you know precisely the conditions that each electrons in the beam will experience in terms of the chi parameters, and you can therefore open the possibility for precision studies of strong field QED. Now, the question is, could we go as high as we want in terms of chi? So if we want to increase the chi, we can increase the beam energy, because it's simply proportional to the Lorentz factor. And we can, of course, increase the amplitude of the fields. And this usually comes with an increase in the beam density. And so there is actually a lot of physics involved in these collisions between the beam and the plasma. And in particular, what I've described as the reflection of the field, it can potentially fail if the beam becomes too dense. For example, if the beam density is larger than the plasma density, or if it's too short. Then in that case, the plasma may not be able to screen properly the beam cell field, and suddenly the chi that you reach is not as high as what you were hoping for. So that tells us that actually, if you want to go high in chi, you need a large beam density and therefore large plasma density to be able to screen. And therefore, the maximum plasma density that you can have in an experiment is important in determining the highest value of chi. And of course, this is one reason why we used a solid density plasma to work with high density plasma. It also means that we can use dense targets like gold and leverage field ionization of the target to increase the plasma density. There is also another effect, which is that actually for these beams, the plasma surface becomes compressed, which you can see here, that the field of the beam is actually pushing the plasma electrons, and therefore it's compressing the surface. And that also helps in screening effectively the beam cell field. And there are other effects related to the shape of the beam between longitudinal and transverse beam size that affects how the reflection works, going from radiative to stationary regimes. Taking everything together, we can find an optimized set of parameters where we use gold, and the beam is going to field ionize the gold. And we used a beam that is actually same transverse size and longitudinal size. And with those parameters here on the top right, we have performed a QED peak simulations shown on the left with the Calder code, and where you see the beam that enters into a 50 nanometer thick gold target. And as it goes through, you see the production in yellow of gamma rays through nonlinear inverse quantum scattering. And those gamma rays can then be converted into pairs through nonlinear Brent-Wheeler. And so at the end, when you get out of the target, you get a relatively large number of electron-positron pairs that have been produced, about 10 picocoulomb of positron charge, above 1 GeV produced in this process. On the bottom of those plots, you see a plot of the chi that is reached from the E and B fields. And you can see that in the middle, you get chi up to 25 that are generated in this interaction. And finally, in the simulation, we've checked that there was about a factor of 1,000 between the number of pairs and gamma rays produced through Brent-Wheeler and Compton over competing processes such as Bremsstrahlung and Bethe-Adler that are not interesting for strong field QED. So that was the situation with a single foil, basically, and that if we are able to reach extreme beam parameters, we could probe strong field QED and perform precision measurement with it. Now, it turns out that we can also enhance the effect using multiple foils. So the idea is that if in between two foils, so the first foil is going to screen and prevent the field of the beam to enter in the foil, if those fields are going to reform in between two foils so that you basically repeat the process at every foil, then yes, of course, you can enhance the effect. If we talk about producing gamma rays through nonlinear Compton scatterings and the beam stays the same, then you would expect that you would just increase the amount of gamma rays linearly with the number of foils. But actually, when you have the collisions, not only you have the emission of gamma rays, but you also have that those reflected fields act to focus the electron beam, so that after one foil, the beam is a bit smaller. After two foils, even smaller. After three foils, it gets smaller and smaller. And that leads to a self-focusing effect from the collisions between the electron beam and the multifoils. That self-focusing effect means that the electron density is going to go up, that the focusing and emission of gamma rays get even stronger, and eventually you can reach extremely high densities that are comparable to the solid density, and you produce very dense gamma rays with a density of gamma that is also close to the solid density. And potentially that can help reach the strong field QED conditions, because the parameters that you need initially, they are not as difficult to reach as the parameters you have at the end that allows strong field QED to be reached. So that's a result of a Smiley 3D peak simulation performed by MPIK group. And so here it's about half a micron beam size and bunch length, 2 nanocoulomb. It's 10 GeV again. And the beam is going to go through 20 foils. So here I have a movie on the right where you see, again, electric and magnetic field. And on the bottom, you see the electron beam and the gamma ray beam. And of course, initially there is no gamma, but you will see that gammas are being produced during the interaction. I'm going to start the movie, and you're going to see that the beam goes through different foils. And Importantly, you will see that the electric field is going to vanish every time you get to the foil, while the B field is going to double at the surface. And inside the foil, you will see that there is no field up to a point where the fields can penetrate if the beam density becomes larger than the solid density. So let's look at the movie. So that's point number one. You see that the fields indeed are reforming between the foils, but every time they get shielded, no electric field, the magnetic field is getting enhanced on the surface, but inside the foil, you see no field. And now we're going to get to soon to foil 6 or 7, where you see that the fields are now penetrating, and this is because the density of the electron beam has become so large that you cannot screen the field anymore with the solid density plasma. At that point, you have actually a very large number of gamma rays that have been produced, and the density of gamma rays and of electrons are comparable to the solid density. In addition to that, it turns out that the chi parameters that is being reached when you have this very strong focusing and so very large density of the electron beam, which enhance considerably the magnetic field of the beam, is that this chi parameter reach 3, and therefore you can also expect here to observe Red-Wheeler electron-positron pairs. If we look at the overall pictures with the result in terms of electrons here and in terms of gamma rays, you see that you radiate gamma rays with energies that are in the thousands of MeV, so we're in the GeV range, and you see a very strong effect on the electron spectrum, that many electrons have lost a very big part of their energy, and this is in relation to the efficiency eta from the electron beam to the gamma rays, which is very large, and after 20 foil, you get 30% efficiency, which is a very large number, which is you just send that beam into 20 foils, and the beam has lost 30% of its energy by emitting gamma rays. It's a very, very big number. So now, it turns out that this important result on using multiple foils to focus the beam, get very dense gamma rays, and potentially reaching strong field QED. That is the initial motivation from an experiment that we are carrying out at the SLAC Facet 2 facility, this S9.4 experiment. And the first goal of that experiment is to show that indeed the beam will get focused, as we were showing here. And we need to consider beam parameters that are not necessarily the parameters that will get eventually by the facility. And if we look at the focusing effect of a single foil, we can see that this critically depends on the charge and on the emittance. And this is what you can see here with different beam emittance. And that potentially you could see an effect with a 3 microns emittance that is very strong. It's comparing the blue to the red curve with a single foil. But if you are at the 30 microns emittance, you don't see such a big effect. And using the multifoil will considerably help to see the focusing effect. And there is also the multiple scatterings in the foils that needs to be accounted for. And that means that in order to have negligible multiple scattering, so it's comparing the black to the blue, using thin foils is important. And finally, if we summarize what is needed, we need low beam emittance, high beam charge, and thin foils to have a clear focusing effect. And in terms of gamma rays, which will be the second goal of the S9.4 experiment, if we don't necessarily get the same parameters as what I presented before, which was half microns in beam size and bench length, it turns out, and that's also in the same paper, that you can still reach fairly large conversion efficiency, about 10% if you have 5 microns transverse size and 1 microns bench length, and 1 or 2% if you have 5 microns by 5 microns in bench length and beam size. So that means that and those parameters are realistic parameters to be achieved by the FACET2 facility, although they are not the parameters that we have today. So now I'm going to move to the experimental side, what we're doing directly on the facility to install the hardware, prepare the diagnostics, commission our measurements, and hopefully take soon experimental data to have an evidence of the focusing in the multifoil. So what we've built is a set of these multifoils, which have holes of 1 millimeter. And so you see this succession of foils. We have this installed. It's aluminum foil, which are 1 micron thick, and there is 100 microns between each foils. And what is currently installed is a set of 40 foils. And so we expect to send the beam in there and hopefully to get some focusing of the beam inside this multifoil target. And the way it's done is that we are basically having a sandwich between the 1 microns aluminum foils and some grit, which has this shape in order to maintain a rigid target overall. So this is being done by preparing the sandwich between foils, aluminum foil and stainless steel grid. And now, as I said, today's beam parameters are not yet the target parameters of the facility. So today we're more at 30 micron beam size and punch length, 1.6 nanocoulomb of charge. And so we've simulated what is expected in that case. So here I'm showing again the field. So here it's the electric field, and a slice of the electric field is shown on the bottom right. And then you see the beam density, which will go through the different foils, and the beam size, divergence, and emittance here on the bottom. So we're going to go through 20 foils, and here again you see the field that reforms and that gets shielded into each field. And here you see the slice of the field being shielded and reforming. And here you see the beam going into the different foils. And overall, what's important is on the bottom left is that actually the beam gets sees a focusing effect. It has not yet been focused because at those beam size and bunch length, the effect is too small to occur over a small propagation distance. But the effect is imprinted on the beam, and that is characterized by a divergence that has increased considerably. And if we go to 40 foils, we see that the effect will be observed after the foil stack. So not inside the foil stack, but downstream of the foil stack. And here we basically have what we expect from early measurements is a foil stack that will act like a lens with, for these parameters, a 4 centimeter focal length. And we expect that the divergence due to this focusing will change from 60 to 600 microwads. And that is going to be something that is easy to measure. So this is installed on the FACET2 accelerator, which consists of the second kilometer of the SLAC RF accelerator. As you know, there is also the LCLS X-ray for electron laser here, and the LCLS2 over here. And in the experimental area, we have first an experimental chamber where the beam is going to get focused. And in this chamber, we have a target mount with gas jets, solid targets, and so on. And we have in particular this foil stack, which is installed. 4 minutes, right?
2 minutes left.
2 minutes, okay. So we go through through a set of quadruples. So the beam goes through a set of quadruples to dipoles to disperse different energy, and then to a diagnostic table at the end just before the beam dump. And there we have a number of diagnostics for gamma rays and for the beam. And this is where we're going to measure the electron beam. And when we measure the electron beam, we're able to set the quadruples to have one axis to be the angles and one axis to be the energy. And that allows us to measure as a function of the energy, the divergence of the beam. And so that's an example of measurements we did with a single foil and trying to commission the measurements with respect to multiple scattering in the foil. And this was a 100 microns aluminum foil. And you see that in vacuum, you get the blue curve. in the foil, you get the red curve and you compare it to what you expect with the multiple scattering, and it works very well. And so that was a commissioning of the hardware and the detectors, and an example of a succession of shots. And now what we will expect when we will put the multifoil is that, so first of all, this is the measurement without the foil, which has small divergence of 60 microrad. And then when we insert the foil stack here, we get a focusing effect, which then leads to the beam diverging towards the screen and to an increase of the divergence that is by a factor of 10 that is expected to be very easy to measure on hard detectors. So if I conclude, I started from the simple case of a single foil with extreme beam parameters that could allow to probe the strong field QED regime with precision measurements. Then I went to how we can leverage the use of many foils to enhance this effect and allow the self-focusing of the electron beam, the production of dense gamma rays, and potentially help to reach strong field QED conditions. And finally, I discussed the S9.4 experiment and its readiness to observe the first evidence of focusing in the near future. Thank you for your attention.
Very fascinating work. Now questions? Okay.
It's a really interesting and simple idea. I really liked it. Do I see that well from an experimental point of view that this is a single shot experiment? So one electron beam will destroy the foil and you have to then shift your target and get new electrons.
Yes, so you're completely right. So at the moment, depending on the beam parameters, you can go from a situation where you do not destroy the target at all, and you can shoot many, many times. This is when the beam is not that good. And so all of these effects will be rather minor or non-existent. This is where we started with the commissioning of the experiments, where we had early beam parameters. Then you move to a case, and this is where we are now, where you don't destroy the target in one shot, but you destroy it over a thousand of shots. So typically, we did the experiment that I showed for the commissioning with 100 micron aluminum. That was just for commissioning, and for 100 microns of aluminum, it took about 1,000 shots, which were to say that every shot we basically drill through the foil by about the skin depth, which was of the order of 100 nanometer in that case. So when we will be using thin foils, as we have in the stack, it will only take, say, 10 shots. And when the beam parameters will get better, as we hope, it will only take one shot. And then it becomes what you've just said. It's a single shot experiment, and we need to move from one point in the foil stack to another. And so this is why we did this design with many holes in the target.
And maybe a second short question. What I expected, if you shoot through materials foils, then you would have some modulation in the beam, some filamentation. Do you, in the simulations, you don't have it because everything is ideal. Do you see some signs of filamentation which might influence strongly the focusing?
So in terms of filamentation, we actually have another experiment which aims at looking precisely at filamentation instabilities of the beam in the plasma. And we look at this into densities that goes from gas density all the way to solid density. However, the parameters that are required to trigger this instability, the filamentation instability, so it's either the current filamentation instability or the oblique two-stream instability. They require a beam density that is quite high if you want those instability to develop over a foil that is typically millimeter scale. Here we go. So we have another experiment where we plan to use millimeter thick foils and hope that if the beam parameters are sufficient, then the instabilities will be triggered and potentially could also lead to the emission of gamma rays, for instance. Here we will rely instead on very thin foils. And so it's not that the instability doesn't exist, it's just that the scale over which the instability will develop is much longer than the amount of materials that we will have on the beam. You have to remember that it's a 10 GeV beam, and so like if you compare it to instabilities that you would have at 10 MeV or 100 MeV, the growth length is going to be much longer as we increase the gamma factor of the beam. That's also why you can't do that with just a 1 micron foil.
Kellen also have a question.
Yes, thank you for the talk. Very nice approach to this strong field QED. So you're going to have electron energies up to 10 GeV, and how are you going to measure the gamma ray spectrum, and what exactly are you going to look at for the gamma ray signal? Are you also going to look at various specific features, for example, for the profile or for the spectrum? And how are you going to plan to do that? I didn't catch very well.
So it depends on whether you talk about the strong field QED IED that I presented at the beginning, which is really at the stage of the IED, and we don't yet have the parameters to do the experiment. Or if you're talking about the S9.4 experiments, where we will also produce gamma rays without necessarily entering the strong field QED regime. If it's the second one, then we have a set of detectors, and I think there are some similarities, of course, with what you have presented. We will have scintillators to measure the angular profile, similar to you. We'll use a set of filters in conversion mode to have some identification of critical energy. And then there are more advanced gamma ray detectors, and there is a gamma ray detection chamber being built. And this is led by the group of Jamie Rosenzweig at UCLA. It's an effort that is facility wide in a sense, because they will implement this for facet 2 that will actually contribute not just to S9.4, but it will contribute to many different experiments at facet 2, including the main strong field QED S9.20 experiment at facet 2. And in there would be a Compton and a pair spectrometer. So two different spectrometer, one for the low energy up to 20 MeV, that's the Compton spectrometer, and one pair spectrometer to go to the GeV range.
Okay, so I think more details will come later on this development, right?
I guess for us, we're still early in the process. So like if you talk about this experiment, the multifoil, the first evidence that we would like is, first of all, to get a gamma ray signal. Because I mean, you know about Compton, and of course you expect a Compton signal, and you're not very surprised. But this is a rather new thing where we are telling that the reflection of the fields on the surface are sufficient to trigger focusing and emission of gamma rays. So just the fact that we would measure gamma rays would already be a great result. And so we don't necessarily need to be at the level of trying to compare different models, for example, of strong field QED and or something similar. We're really at the point of just demonstrating first that we are producing gamma rays, and then we can also demonstrate that there is a focusing that we gain from the focusing in the gamma rays by showing, for example, that the amount of gamma rays that you produce is not linear with the number of foils, but the amount of gamma rays that you produce is going up as the electron beam gets focused. So in this experiment, there are many like intermediate steps because we start from nothing. At the moment in the experiments, we have no experimental proof that we produce gamma rays in this way or that we focus the beam. We think it's going to happen from the theory. We are quite confident it's going to happen, but it has never been done in this way. So our first steps are not as advanced as what you're talking about, which would be having very precise measurements of the gamma rays to be able to compare two models. But this will come later for sure. And there are developments which are taking time, which I'm not leading. It's a group in UCLA that are leading this development of a gamma ray detection chamber.
Okay, I see. Yeah, thank you.
Okay, I'm sorry, we are 10 minutes late, so I think it's time to move on to the next talk. Next talk, our speaker is LPHYS' from Ümel University, and he will talk about the vacuum laser acceleration of electrons from nanotips.
Thank you very much for the introduction. We did different experiments that I will show later. Here in the background, you see a picture where you see some tips. Believe me, the very end I will show later is very sharp, below 100 nanometer diameter. And here you can see how the laser hits such a tip. I mean, this was a cooperation between our university and the University of Gothenburg, and two different groups there. So I will first motivate a little bit the work, why we wanted to use originally nanotips. This work was done, the first part, a few years ago. You could hear a talk yesterday from Ishai Pomerantz about something similar. Here we did, in the beginning, mainly the motivation was connected to the nano targets. Then very shortly, I will introduce the lab and or upgraded laser system. And then I will speak about the first results. And then we'll, in the second half of my talk, I will speak about the part of this process and the new experiments connected to vacuum laser acceleration. Here I will introduce more accurately the vacuum laser acceleration state of the art. And I will close with conclusion and future research. So originally, nano objects were used, or are even nowadays used routinely with low intensity lasers. For example, here you can see a result where they shoot onto very small spheres with low intensities and measured the generated electrons. Probably you can read the numbers. These are on the electron volt range, up to 50, 60 electron volt, and they measure the electron spectrum as a function of the so-called carrier envelope phase, which is shown here. The laser pulse envelope is the blue, the laser pulse duration only typically 1 to 2 optical cycles, and the carrier is the red, and this position of the maximum of the carrier relative to the maximum of the envelope is the carrier envelope phase. And they could observe such an interesting dependence. Later, at higher intensities, say isolated targets were not investigated, not used, but such a nano rods, as you can see here, were investigated, and they observed much higher absorption with monorod target than with flat target. Or gratings were also irradiated, where the nano is this extension in the perpendicular direction. And when the incidence angle was good, then they observed along this direction increased electron emission. This is due to the generated electron plasma, surface plasma waves. We correspondingly try to combine these to use isolated targets and generate orthosecond a few mega electron volt high charge electron beams. Furthermore, nanoplasmonics at relativistic intensities, especially with isolated targets, was a very important motivation to investigate what can be reached. And also the orthosecond control of matter with the light, for example, the carrier envelope phase, we can change the light field with light waveform with orthosecond precision. Short summary or review about the former results, let's say, so that this nanophotonics regime is in this one part of this review, which appeared recently. So about our laboratory, we are in Umeå in Sweden, as you can see here, and a little bit about half of Sweden. This is probably the most northern high-intensity lab in the world. we have a very special laser system, the LPHYS' synthetizer 100. Strictly speaking, it's an optical parametric synthesizer. You are probably you're familiar with the CPA technique. If you combine that instead of laser, it's optical parametric amplification. That is the optical parametric sharp pulse amplification technique. We could hear also earlier talk about that. And we used this in combination in two stages, where one stage amplifies only one part of the spectrum, 700 up to 1000, 10,020 nanometers, and the second stage is optimized, pumped here the second one, the third one, and this is optimized from 580 up to almost 700 nanometer. And this way we synthesize a broader spectrum, which allows the generation of sub-2 optical cycles, which is very important if you want to generate isolated optosecond pulses. Here you can see also a photo, by the way, of the electron chamber, double chamber. Good. So about just very shortly about the laser source. In fact, this is the present status of the laser source because we upgraded this. This is the most intensive cycle system in the world. It has around 430, 500 millijoule energy, depending on whether you optimize for contrast or for energy. You can see the beam here. It's has a quite special color, something like orange. It's relatively stable, 0.5, maximum 0.8% is the RMS energy stability. It has a reasonably good beam profile. After amplification, about 23 millimeters, and the spectrum about 580 up to 1020 nanometers. And this corresponds to a Fourier limited pulse duration of about 4.2 to 4.5 femtoseconds. Here you can see the red is the measured, and the blue behind that is the Fourier limit. Practically, here we completely reach the Fourier limit. 10 Hz repetition rate and about 100 terawatt peak power. If we focus tightly with an F number of 1 of axis, then we can reach about 10 to the 21 watt per centimeter square intensity, which corresponds to an EMF of 20. The carrier envelope phase on the front end is stable, and we are working on the feedback loop, which is almost ready to stabilize the full system. Having said that, I have to mention that in the results that I will present, a former version of the laser was used, which has about 6 times, or had about 6 times lower energy and a little bit longer pulse duration, still shorter than 5 femtoseconds typically. So 4.5 to 5 femtoseconds. So about the former experiment, we used nanotips as shown here and focused the laser tightly on them and generated electron beams which propagated in 2 directions. We detected them with scintillating strings in the 2 directions. The left one, you see, it was a little bit bigger than the right one. This will explain the results later. And the laser propagation direction is 0 degree and minus 90 up to plus 80 degrees. We could observe the angular distribution. So we used nanotips. Here you can see one with a diameter at the end about less than 100 nanometer, about 100 nanometer. The full laser spot size is here in comparison. One laser destroys the nanotip completely, so for the next shot we have to shift in another one. As I mentioned, we measured the angular distribution. We measured also the carrier envelope phase in certain experiments, and we measured also with a high resolution low energy electron spectrometer the electron spectrum. So the results, we used first to measure the angular distribution and the maximum intensity. It was a little bit below 10 to the 20 watt per centimeter square. Then we decreased the intensity by increasing the pulse duration. And you can see that as the intensity decreased, the electron beam propagated more and more to the left side, so further away from the laser propagation direction. If we plot the results as a function, so the emission angle as a function of the intensity, the full symbols indicate the first moment of this distribution, and you can see that it was increasing with decreasing intensity. The empty symbols show simulations, and they are peak simulations, and they are in reasonably good agreement with the results. Furthermore, we also did 2 different tests. Namely, we shifted these targets out of focus, and this way we irradiated a larger area, and correspondingly the intensity was lower. And this shows that in this case, compared to the similar intensity, we observed lower emission angle, so nearer to the laser axis. And as well as if we use the larger target, by shifting up the target, then we observed also lower angle nearer to the laser axis. And this was interpreted in a simple way by two effects, dominantly by, we call this vacuum laser acceleration, where at higher intensity, the electron energy is higher, and correspondingly, the electrons propagate more forward, while at low intensity, it's more onto the side perpendicular to the laser. However, and these results could only explain by this, the Mie effect, which is intensity independent, for a certain size of the target, the electrons are, the field enhancement is maximum in a certain direction, and correspondingly the electrons are emitted in that direction, and the smaller the target, it's more and more perpendicular as shown here. So, for example, 100 nanometer radius or 1 micron radius. And the combination of these two effects can explain these observed angular distribution results. Good. We measured also in this first experiment the electron spectrum in 45-degree direction, and I showed here two results, and you can see that the average energy was about 4 MeV, but the peak energy is extended up to 9 megaelectron-volt. We measured the charge from the angular distribution. We could determine how many electrons we had, and you can see the full symbols. The full maximum peak in intensity, we observed about 100 picocoulomb, while decreasing the intensity, the charge approximately decreased linearly. The simulation showed some similar trend, but slightly lower charges. This is we were a little bit conservative with the laser intensity in the simulation. And at a very low intensity, others did something 7 orders of magnitude lower intensity experiments, and they are also in reasonable agreement with this linear scaling, as you can see. Good, the carrier envelope phase of wavefront dependence. I introduced the wavefront before, and here you can see two angular distributions already from a new experiment, and you can see for a certain carrier envelope phase there are more electrons on the left side, while another one there are more electrons on the right side. These in the former old experiment are shown here. Practically we averaged over many shots, about 72 shots, and then took one certain shot and subtracted the average value. And if you can see that there are more electrons on the left, while if we change the CEP by pi, then there are more electrons on the right side. When we calculate the so-called oscillometry parameter, charge on the left minus charge on the right side, divided it by the sum of them, and plot it as a function of the carrier envelope phase, then the full symbols clearly indicate a carrier envelope phase dependent electron emission. You can see also the corresponding simulation, and here in the simulation we were a little bit conservative again with the pulse duration. It was about 5 femtosecond, while obviously the experiment it was shorter, therefore the dependence is stronger. We also investigated the first moment on the left side, and that is plotted here as a function of the carrier envelope phase. And even here we can see the dependence of the exact propagation direction as a function of the CEP. Even you can see that it is a little bit anti-correlated with the charge. So when the electrons propagate the nearest to the axis, then we have the lowest charge. I can explain that separately. I don't want to go into these details, but even this we found out must depend on the laser intensity. So it's a clear asymmetry in the electron field as a function of the CEP. Also, the electron propagation direction depended on the CEP. This is the CEP-dependent relativistic interaction. Not only nanophotonics, it was in fact for electrons the first CEP dependence at relativistic intensities. We did peak simulation to understand a little bit more the process, and here you can see the tip from the top. And then at a certain time instant, the electric field maxima reaches the target. And here you can see that there is a certain field enhancement, especially relevant on the other side. And electrons on one side, you can see this dark area, are removed by these huge fields. And then in a second step later, where this field enhancement and the effect of this monotip is already removed or disappeared, then the electrons are running with the laser field and gaining further energy. So the first we term the monophotonic electron emission step, while the second is the vacuum laser acceleration step. It's very important to mention this is a sub-cycle, it's more correctly than sub-half cycle regime, because these electrons are removed at the maximum of the electric field and they are fall a little bit back, but still within the same half optical cycle, they remain within the same optical half cycle and propagate with the laser. And the simulations indicated that this electron energy increase is up to about the Rayleigh range. We did also simulations up to 7 times the Rayleigh range, and then we saw that up to the Rayleigh range it increased. In certain simulations, we could also see the 2 different steps, how the electron energy increased very fast in the first one, and then later a bit slower in the second step. The electron properties were about 10 MeV, and the bunch duration, you can see, for example, here, the distance is about 2.5 femtoseconds, it's 150 nanometers, and the duration is about 200 watt per second. And the charge were a little bit lower than the measure, but still about 40 picocoulomb in a certain step. This was published originally in 2019, and later we had another simulation to investigate some details more in 2021. Another interesting feature is the accelerating field, which we can easily estimate from the simulations. Here you see the energy as a function of the position. This is the distance from the monotip to the electron bunch, and from that you can determine about 5 to 10 terawatt per meter in the first step, and here in the second step about 2-3 terawatt per meter. Experimentally, we could not separate these steps, but what we could observe is the final energy, 9 MeV, and from the simulation, we know that the energy increases maximum up to the Rayleigh range, which was carefully measured in 4.8 micrometer, what we observed, and this corresponds to about 2 terawatt per meter, which is at least about 10 times stronger field than by laser field acceleration. Good. So we saw that the second step was vacuum, could be explained by vacuum laser acceleration. Here I would like to shortly introduce vacuum laser acceleration. There are many theoretical papers about that. Here I cited only a few where they clearly showed that it is possible, but there were in some cases difficulties. For example, Salomon paper or the Popov paper clearly indicated that many simplifications like the Gaussian beams are not optimal for this vacuum laser acceleration simulation. Experimentally, it was much more challenging. Up to now, there are only 3 published experimental papers. First is Stevenet paper, where they shoot onto plasma needles on a solid target, and the reflected beam, in the reflected beam, they realized the vacuum laser acceleration. In fact, the electron distribution had a hole, which was a very important signature of vacuum laser acceleration, because the laser itself, as it propagates back, kicks out the electrons from its path, and this generated the hole. The second was our work that I just presented. In fact, it was not clearly observed in this hole in our case. And another work was recently published where they used thin foil, and injection was made by the relativistic transparency in this foil, and they also observed this hole in the electron distribution. And this triggered the question, now, do we have real vacuum laser acceleration, and why don't we see this hole? And so this hole was the motivation for further experiments in the vacuum laser acceleration process. So here we again focus slightly the laser pulse. We had even a little bit higher than 10^20 watt per centimeter square, and we observed with a scintillating screen the distribution, and we could insert a 1 millimeter lead foil, which cuts electrons at lower energies. Another very important change, we started to use also f^3 focusing. And then here you can see the distribution. First, if we use the lead foil, then charges typically between 7 up to 100 picocoulomb were observed. And I picked the 7 picocoulomb because here very nicely you could see just 2 electron beams to the right and to the left direction. If we now remove the lead, then we had much higher charges, 500 picocoulomb up to 1.5 nanocoulombs, and still about 40 millijoule laser energy on target, I have to mention. And here, with the f^3 parabola, we could already observe the hole, which was a clear agreement with former measurements, as well as I will show you later, or newer simulations with f^3 parabola. But we did another measurement without the lead. We decreased the incident beam diameter by a factor of 2, with that effectively we had an f^6. And you can see that here the hole became smaller and corresponding to the expectations. So the VLA generates a hole in the distribution. Even we could observe that with this f^3, and this hole depends on the f number and was smaller with f^3. So high energy electrons are not much affected by this hole, by the way. Then we used also f^1, not only the f^3, and measured the electron energy as a function of the azimuth angle, so from 0 up to 40 degrees. And you can see that for the f^1, we could see up to 15 MeV in 10 degree, and this decreased with the angle, but not so strongly decreased. By the f^3, interestingly, we observed similar electron energy in the 10 degree direction, but it decreased very quickly with the angle. It is very important that the laser energy was the same on target. That means the intensity in this case was 10 times lower, and still we managed to observe about the same electron energy. It is a very unexpected result. In simulations, we were able to reproduce these results, as you can see, with a relatively good agreement. So most energetic electrons propagate about 10 degrees, and the higher energy electrons also, so these are also propagate approximately in this 10 degree direction. There are fair agreement with the peak simulation. Longer focusing, so 10 times lower intensity, generates similar electron energy, and this is clear indication of vacuum laser acceleration, which we also could track in the simulation. Again, in the simulations, we observed the angular distribution. First, the f^3, the measurement is here without the shield and with the shield. And you could see practically high energy electrons. There are only these 2 spots, while lower energy electrons, here you could observe a hole and corresponding to the measurements. In fact, we did many further measurements, and we could identify also a hole in the f^1 experiments for certain shots. You can see that is here, while when we use the shield, then again there are 2 electron beams were observed to the right and left directions. And you can see here also the corresponding simulations with high energy electrons and low energy electrons. In this case, also this hole was much larger, corresponding to the fact that the tighter focusing has a much more divergent laser beam, and that makes a much broader hole. So again, fair agreement with simulations regarding angular distribution, hole in the electron distribution, even this f^1, and this again supports the vacuum laser acceleration idea. So very shortly, I would like to then summarize the results. So few cycle optical parametric synthesizer is an optimal source for, among others, relativistic nanophotonics. Relativistic nanophotonics allows the study also in a second step of vacuum laser acceleration. And there are good agreement with the expectation for estimations for vacuum laser acceleration. Correspondingly, we have to do further work using, the first step is using the upgraded laser, which has up to an order of magnitude higher intensity, 6 times higher energy, slightly tighter focusing probably, and shorter path duration. And here the expectations are based on the simulations from Wojtek are about 30 to 50 MeV electron energy, and still the same very short electron bunch duration. Then the next step is the temporal characterization of these electron bunches, which is quite challenging because, as you could see, the electron spectrum is more or less flat top-like. That means you have also slow electrons. That means during propagation, these electrons will spread and they quickly get longer. Plus, also space charge effects can make during propagation longer. But up to a few times the Rayleigh range, and simulations indicated up to 7 times the Rayleigh range, definitely this short duration remains. And there we have an idea how to measure it. And a new theoretical model of, we are working also on a new theoretical model of vacuum laser acceleration, because some estimations based on the plane wave are not very well working in the case of focused beams. Plus, an application of these electrons very near to the Bell generation is Thomson scattering, where we did some basic estimations and they indicate few kilo electron volt up to 10, 20 kilo electron volt, from 2, 3 kilo electron volt per second X-ray passes. Good. Is that I would like to thank you for your attention. And here you can see former co-workers and some new co-workers that contributed or will contribute to the results. Thank you very much.
Okay, thank you. Very nice talk. It's time for question. Okay, Aishi.
Yeah, very nice result, and interesting new results. About the new experiments, was the radiation was of exactly the same type of target, the same nanotips?
Yes.
The same effective size?
Yes, practically the only difference is that formerly they were commercial and we started to produce them ourselves. And we could, in some cases, produce even targets. I think I don't have the photo of that, only the original. Here we could produce even targets where this end was much smaller, so maybe down to 20 nanometers. But we don't see, I mean, as the laser is much larger, we irradiate also larger areas, so thicker areas, and therefore we don't see a significant effect of that. So electron emission is not only from the end, but everywhere where we irradiate, and therefore whether it's 100 nanometer, 20 nanometer, that is not relevant.
Mm-hmm. And in this vacuum acceleration regime, do you also have a way to estimate the target size from the separation angle of the electron jets?
Not really, because dominantly, like here you can see, dominantly the angle between the two is determined by the vacuum laser acceleration, and not so much the target size. Target size, if it's wavelengths or micrometer or below, influences it a little bit, but the dominant effect is the vacuum laser acceleration. And I have to mention also the CP influences this a little bit. And therefore, maybe it's not impossible to do that what you asked, to estimate the target size. But the problem is that you have to measure also the carrier envelope phase for every shot, because that has a very significant effect. Plus, you have to very precisely focus and know the intensity, because the intensity will have a very strong effect on the direction.
Very nice. I have one more question, if the chair allows.
Okay.
Yeah. So you mentioned in your very first slides that you have some trade-off between energy and contrast.
Yes.
Yes. Can you just in one word just explain what is the trade-off, and do you think that you're seeing any effects of contrast, of insufficient contrast, or dependence on contrast in these experiments?
Yes, so the trade-off is coming from the fact that if you, in the OPCPA system, or the OPS system, if you block the seed before the first amplifier stage, then you still generate optical parametric fluorescence. And if you don't optimize typically mean turn down the gains, especially first stages a little bit, then this parametric fluorescence will be will have a significant effect, and on the 10 picosecond temporal range will be high. And we recognize that formerly these experiments were done with 2 pairs of amplifiers, and correspondingly it was less critical. Now with 3 pairs of amplifiers, we have strong saturation in the last one. This got much more important, and we could observe if we block the seed, then we overestimate this background. And this background was on the millijoule scale by 500 millijoules if we optimize for the energy, while it went down if we optimize for focus, or turn down the gains, then the energy was about 430, this range. And in that case, it was, even when you block the seed, only a few tens of microjoules. And in fact, that is less if you amplify, because the main pulse removes energy from the parametric fluorescence. So this is just a good measure, but not accurate. So that means, and formerly we had also a few tens of an order of 10 microjoule, what was overestimated in the parametric fluorescence, formerly with the 2 stages and the lower energy. So LPHYS 20. And now to answer the second part of the question, we indeed, if we, with the former, we turned up and we generated a little bit more on the order of 100 microjoule, then we started to see that the angular distribution became completely different, and that we clearly indicated a bad contrast, while when we had the normal contrast with 10 microjoule, below 10 microjoule parametric fluorescence, then it was clearly identified that the distribution is different, and you could see nicely the 2 electron beams. So indeed, contrast is a very important point, and we could identify even the PhD student, Andres, has in his thesis some investigations about this, and we could clearly optimize the contrast easily, and the standard contrast was good enough. Though degraded contrast already showed effects of effectively, these are targets expanded, and we saw that also in simulation that the expanded target is not generating nice electron waves.
Yeah, thank you. Very nice results again.
Thank you very much.
Thank you. More questions? Okay, Christoph.
Laszlo, very nice talk. Maybe you can elaborate quickly. You mentioned this extension on the series. Is this straightforward? You mentioned, like, I guess, pulse shape effects and so on, that, I mean, you were working with a very good team. So is that something feasible, like by Shika and so on, that they could include it to the code? The things you
very
need?
Good question. Up to now, if I summarize shortly, there are big differences between a plane wave and a focused wave. And correct simulations, it can be peak simulation or tracking simulation that which I showed yesterday, they include this. Though if you use a Gaussian beam, then that is dangerous. But the main point was what I mentioned originally with the new theory is not just this. The main point was that if you use the plane wave, then the scaling is completely different. Namely, it scales the maximum electron energy scales with the intensity. While in all simulations, I didn't plot that, but these simulation results, when here you can see the maximum energy, and we investigated this as a function of the focusing, practically in both papers, and they were proportional to the field. And also, if we take the theory papers about vacuum laser acceleration, then the big conclusion that the longitudinal field has an effect. And this is what we are investigating now more accurately. So our conclusion was that the models like calculation with correct focusing or simulations with correct non-Gaussian rules, definitely they are good. But the interpretation of these results are not correct. And this is what we are also working on. So one point is to eliminate the Gaussian approximation, and second point is the correct interpretation of the results. I will not report on that because we are still working with Shika and Arkady and others, but that will be a separate publication. And we are now working on a publication about these new results, experimental results, and also on a publication about the model for vacuum laser acceleration.
Super. Thanks a lot. Sounds good.
Okay, if no more questions, then let's thank all the speakers to contribute and all the audience.
Okay, so see you tonight then, hopefully.
See you.
Bye-bye.
Bye-bye.